This lesson picks up on where we left off in class with regards to the symmetry of a function. We define symmetry in a visual context by looking at graphs and deciding if even functions came as a result of a reflection through the y-axis. And also we learned that if a function could be rotated about the origin and look exactly the same following that rotation, then the function would be classified as being odd. Okay, so let's see if we can also do this algebraically. A definition for determining if a function is even or shows even symmetry is the following. If f at x is equal to f at minus x. Based on what we had seen yesterday in class, we talked about the effect of taking the opposite of the x values, and the result of that graphically was a reflection in the y-axis. And I think we can definitely see that by looking at graph number 3, which was taken from the first slide of yesterday's lesson. The equation that's below it defines the graph of that function. And we're going to use the definition that we have above in order to prove that it is even. So let's give it a try. Okay. When we begin our proof, we'll start with a statement that if the function is even, then f at x is also going to be equal to f at minus x. So what that means is we are temporarily making a statement that we're going to change the x value. Okay, so where we see positive x, and we can see that all the way along here, we're actually going to substitute minus x along the way. Okay, you don't need to write that down right now. I'm going to show you behind this screen shade momentarily. Okay, so let's go ahead and make that substitution, and let's make sure that we do add parentheses around the negative and the x, because it is becoming the base of each of those powers. So we must apply the exponent to the negative as well as the x. So if we carry on to the next step, take note of what happens when you have an even degree. Okay, not even symmetry, but an even degree. You look at each term, we have a 6, a 4, and a 2, all being even numbers. The effect of using those as powers makes each of the powers positive. So we now have f at negative x being equal to the same statement that we began with, which is this one here. So at the end of the day, what we can do is, because the right-hand sides are equal, we can make a statement that f at minus x is actually the same as f at x. Okay? And in conclusion, f at x, or since, this symbol denotes the word since f at x is equal to f at minus x, f at x is even. Okay? So on the other side of the fence, we have a proof whereby we can show that a function is odd. Okay. I'm just going to circle back for a moment to yesterday, if you don't mind, very briefly. If you recall this from yesterday, okay, I'm focused down here in this region, graph number 2, you can see how we had transformed the original graph from the graphing calculator and came up with f at minus x and minus f at x. When that occurs, the function is said to be odd. So that's the algebraic definition that we're going to carry forward into our next proof. So you can add this definition to this page. That is, if a function is odd, f at minus x must be equal to minus f at x. So let's take one of the parent functions, the reciprocal function 1 over x, and we'll use the definition to show its truth in being odd. So our first statement goes as such. If f at x is odd, then f at minus x is equal to negative f at x. So what that means is that as soon as we make that statement, this minus x is then going to take the place of x in our formula. Okay. So before we move forward, I just want to bring to everybody's attention that sometimes there's a misconception that when we start doing these proofs, is that we're trying to solve an equation. And I just want to let you know that we are not solving equations. We are predominantly focused on taking the right-hand side and manipulating it. Okay? In this situation, we're working with symmetry. There is no need or no significance for us to do any work with the left and the right hand sides. The work is to be done on the right hand side only. Okay? So let's move forward with that in mind. So what we need to do at this point in time is we need to try to get ourselves to the right hand side of that statement. Because if we can, we could show that the function's odd. So have a look at what we have right now. Okay? At this point in time, I'm just going to get rid of this. Whoops. I'll put that there for now. If you look at what we've got, okay, this portion here minus the negative is the same as what we have here, less the negative. Okay, so we almost have a true statement. That is one that looks like this. So in order to make it look more like that, it might be worth our time to factor the negative out. That is to put it in a different position. So let's see what that does. Okay, so we pull the negative out front, okay, which in a more complex example would be like factoring a negative out front. And you can kind of see now, here's our f at x, okay, and the minus is here out front. Okay, I apologize for the dark color, but there is a negative under that highlighted area. So what we've just done is shown how the function is odd. So let's make a conclusion that since f at minus x is equal to negative f at x, the given function is odd. Okay, well, let's journey into one more. Okay, another example. You most likely have the slide for this. If not, I apologize for lacking the copy, but it is a rather short note, so you could transfer that onto lined paper. Here's the problem. Determine if f of x is even or if it is odd. Okay? Now, one thing you might want to do when going through these video lessons is to temporarily pause, go back, review, reflect, try to make some connections for yourself. And in this case, you might actually consider trying this problem out first and then playing through. Okay? So when showing or proving a function's symmetry, we often start with looking for even symmetry. Okay? And if we find it, great, we stop. If we don't find it, then we'll progress to looking for odd symmetry. If we find it, great, that's wonderful. But if we don't, then we'll have to conclude that the function does not have even nor odd symmetry. Okay? So let's have a go at this. Okay, so I'm rewriting the function equation, and recall that when we're showing even symmetry or trying to prove even symmetry, that we do need to substitute in minus x where we have x. So let's do that. So in goes minus x in parentheses. We'll square minus x, and we're also going to cube minus x. So when you square minus x, the result is x squared. And when you cube it, the result is minus x cubed. Okay? So if we take a moment and we look at what we have so far, note that this statement is certainly not equal to that. And because it's not, what we can say is that, let's choose a different highlighting color here. Let's go with that. What we can say is that f at minus x is not going to be equal to f at x. Okay? So here's our conclusion. Function is not even. Well, let's go a step further. Okay? We're going to begin the same way, okay, by substituting in negative x into the function equation. Okay? So let's work our way through that. Okay? We have the same expression that we did in the last proof. The only difference this time is that to show that other reflection is we're going to have to try to pull out the negative. So let's factor a negative from both of those terms. Okay? And when you do that, you change the sign, okay, of everything inside of the bracket. So we end up with minus x squared plus x cubed. Well, looking at this, okay, you can see how we have the negative pulled out, exactly where we wanted it. But if you look at what's left over on the inside, this is by no means equal to f at x. So if it's not equal to f at x, then it looks like we cannot say anything but f at minus x is not equal to minus f at x. And because of that, the function is not odd. Now, just looking back at an earlier part of the solution, I can see how I've got the right symbol here, but over here, I should be putting in a not equal symbol there. So our conclusion has to be that f at x is neither even nor odd. Okay, so we're approaching a 15-minute mark in terms of this video, so I think we're going to close it there. You're going to find that in your homework, which is posted on the course website, page 23, question 4, I believe, is going to ask you to show algebraically if a function is even or odd. So you can use these examples to do so. Tomorrow, in terms of warming up, it might be a combination of taking up homework and or actually having you try to prove the symmetry of another example. Okay, until then, good luck with the work tonight, and bring any problems forward to me outside of class or at the beginning of class tomorrow.